Hi, it's Ben from 3dtech.xyz. Going to be looking at the electronics and software and firmware required to control a lightweight CNC routing machine. We'll be using the open source GRBL motion control firmware and the 3dtech GRBL all-in-one card. The GRBL related information will be relevant to most dual wire motor routers such as the Shapeoko, Xcarve, Ox and others. The electronics information, while centered around the GRBL all-in-one card, is mostly relevant as well to other electronic options such as the Protoneer CNC Shield, the Syntheus G Shield, our own CNC Shield, or your own Arduino and external driver combination. I will introduce the individual pieces of hardware, then look closely at the all-in-one card, the GRBL firmware, and then we'll bring them together to set up a CNC router. For most any flatbed CNC router, you'll be looking at hardware similar to what we have here. Some stepper motors, drivers which in our case are integrated into the motion controller board, limit switches, of course a power supply, and other associated electronics items, connectors and heat sinks, fuses, USB cables, etc. Let's take a look at the stepper motors first. The motor you're looking at here is a NEMA 23 76mm stepper. The NEMA 23 standard specifies dimensions on the front face of the motor. The length I don't believe is part of the standard, and that's why I've specified it as 76mm. The 23 in NEMA 23 refers to 2.3 inches, which must have been the diameter of a stepper motor in its round form, as with the square stepper motors, the closest measurement to 2.3 inches I can find on the front of this motor is 2.2 in the width of the motor itself. The most common steppers that we will come across are a two-phase 200 step per revolution motor, meaning that there are two coils inside the motor and that there are 200 unique steps or detents in a 360-degree revolution of the motor. This one's a 3.2 volt motor with 2.8 amps per coil. The 3.2 volt rating on this motor is nominal only. The manufacturer does not expect us to run this motor at 3.2 volts. They're stating that at 3.2 volts the motor will draw around 2.8 amps per coil. It's important to note that we hand stepper motors a voltage and they draw or take a current. We don't hand them a current, they draw it, and when running them at a higher rated voltage, we need to actively manage the current limiting, which suggests that the motor will want to draw a lot more current than it can handle at that higher voltage, and we'll have to limit how much can be drawn. Google stepper chopper driver for more information on how this works. What's important to know is that the drivers that we use running this motor will manage the current limiting for us. We just need to give them a signal as to where to limit the current. These steppers have two coils and 4 wires. 2 of the wires per coil. Our steppers all have black-green as one coil and red-blue as another. One interesting note about stepper motors is that they should turn fairly freely. However, if several of your wires are connected, you may find that the motor is breaking and is very difficult to turn. We get the odd support call when one motor in a batch of say 4 doesn't spin as freely as the others, and it's always because a couple of wires are touching. That fact that the motor breaks when the coils are shorted actually makes it very simple for us to work out which wires are connected to which coils, which wires are pairs. If you take any 2 wires, for example black and red here, and short them out, if those two wires were a pair, the motor should become very difficult to spin, which it's not, leading me to believe that they are not part of one pair. Black and green, however, which I know is a pair, will result in the motor becoming very, very hard to spin. So we can assume that blue and red are the other pair, and connecting those ought to make the motor even more difficult to spin, which it has. You'll find a resistance measured across these pairs for this motor somewhere around 1.3 ohms. And that is convenient for diagnosing problems with your wiring when these wires are running through your drag chain and are no longer visible. Measuring a resistance between these two wires that is not somewhere around 1.3 ohms would let you know that there's some issue with the wiring, whether it's a short or a break, and can help you diagnose why a motor is not working as expected. One of the signs that a motor is not wired correctly is the motor not moving in the correct direction, or hesitating and moving and choosing an arbitrary direction when it's instructed to move. This generally means that one of your two coils is not connected. One of the last interesting points about a stepper motor is that if it's moving in any direction and you would like to reverse that direction, you're generally able to choose one of the two pairs and simply swap the order of the cables in that pair, and the motor will move in the opposite direction than it had previously. You don't need to swap both pairs or both wires in both pairs. Simply swapping the position of the wires on one pair in your connector will generally make the motor spin in the opposite direction. The next item is the limit switches. We like to use this Omron lever style micro switch because it's got a great snap to and open, which doesn't leave a lot of middle ground and bounce. It is a contactor switch, so there will be some bounce, and if you're chasing a cleaner signal, you might look at the photo interrupter switches that use an infrared light source and a receiver, and will let you know when an object interferes with that transmission of light. This switch does a pretty good job for what we're looking for though, which is to allow us to home the machine and find a 0 point, and also to let us know when the machine has gone out of bounds. This switch is shown wired in normally open configuration, which is probably not the right way to manage a limit switch, being that it is a safety feature and should be wired normally closed. The way this switch interacts with GRBL is that GRBL will be pulling this line high to 5 volts, and we've connected this line down to ground. When the switch is depressed, it will short out these lines and bring the voltage down to ground, letting GRBL know that there's a problem. It doesn't, however, send any signal to say that there is no problem. A better way to wire this switch would be between these top two terminals, which would be normally closed, meaning that at all times GRBL will be seeing this switch pulling the voltage down to ground and only lets 5 volts pass when the switch is depressed, which would be more like saying everything's good, everything's good, everything's good, we've got a problem. Instead of when it's wired now and normally open, it's saying, oh, I don't know, I don't know, I don't know, I might not even be here, oh yes I am here and there is a problem. Seems to be a little bit of a standard to wire them normally open, even though I don't believe it's the correct way to do it. So I'm going to leave it the way it is, wired normally open. Now we'll take a closer look at the GRBL all-in-one controller. We made the GRBL all-in-one due to several limitations that we found and lack of functionality we found with existing GRBL related hardware options, some of which were the lack of a 0 to 10 volt output for VFD or VSD control, access to the error pins on these GRB8825 drivers, which is for some reason ignored on most uses of these drivers, the use of non-replaceable or no fuses, and a lack of filtering for all of the I/O ports, which leads to no end of trouble. You can Google limit switch errors to see how that plagues hobby CNC. We're also looking for an integrated and clean, easy to set up electronics option. And this card integrates a Atmel 328P processor, or otherwise an Arduino Uno, 4 GRB8825 drivers, RC filters for all input and output, and a 0 to 10 volt and PWM output signal for controlling your spindle speed control. We have limit switch and driver error LEDs, which helps in setting the card up. It also has provision for a 40mm fan to be mounted above the GRB8825 drivers to help manage the heat. I'll go through the steps to set up this card physically before moving on to tuning it and setting up GRBL to run with it. First thing we want to do is connect a jumper to JP1, which is hiding down here under the control port. The only reason for this jumper's existence is that it needs to be removed when programming the card via the ICSP header. The Z limit switch shares one of these programming pins, and so whenever this Z limit switch jumper is connected, there is filtering happening on that line, which interrupts the programming of the chip. So this should always be connected during your normal use of the card. You don't need to disconnect it in order to update GRBL via the USB connection, only if you're going to use the ICSP header. We're also going to put a jumper on JPs 4, 5, 6 and 7, which allows us to get access to the error pin on the GRB8825 should we want to use it. I should mention that this information is all detailed on the GRBL all-in-one pinout page, which can be found by following the link on the bottom of this card. A heatsink is now stuck to the top of each of the GRB8825 driver chips. These chips have a pad on the bottom of them, which is where most of the heat comes out of the driver. There's also a pad on the top of this control board that is soldered to that power pad on the bottom of the chip. And so, in fact, more heat is sunk out through the bottom of this card than is through the top of the driver, and it would be more of a valid setup to instead, or as well, put heat sinks on the bottom of the card. Next, we want to set our micro step-in rates. For the X and Y axis, we're going to use 1/8 micro step-in. This information, shown on the all-in-one connections page, can also be found by Googling the GRB8825 driver data sheet. We're going to set jumpers 1 and 2 to the on position. These are microstep settings 0 and 1 on the GRB8825 driver sheet. So for the x-axis, jumpers 1 and 2 up. For the y, 1 and 2. Since we're sharing the Y signals over to the A driver for the second Y motor, we'll also put 1 and 2 on for the A. Our Z is using half microstep, and so just the first switch. You can set it up with other microstepping rates, however, eighth, and half is the standard setup. Now I mentioned that we're using the A driver to run our second Y-axis motor, so we need to instruct the card to duplicate any step or direction signals sent to the Y motor also over to the A motor. We do this with 2 sets of dip switches down the bottom here. The first dip switch is your direction and the second is your steps. By flicking up the middle of each, we're instructing the card to send over direction and step signals from the Y axis. Make sure only the center switch is pressed up for a dual Y axis machine. The next step is our current limiting. As I mentioned before, we have to limit the amount of current that's able to be sourced from these drivers when running the motors at a high voltage. These trim pots located below each of the drivers are current limiting trim pots. So while it might make sense that dialing them clockwise up is delivering more power to the motors, think of it instead as dialing them up is dialing up your current limiting and therefore limiting more current from the motor. And so dialing anti-clockwise is actually allowing more current to be drawn from the driver. Initially, we'll leave them at around their midpoint and tune them further a little bit later on. Next step, the fuse and the fuse holder. There's a mounting pattern here for a 40mm fan. The fans always blow towards the sticker on the bottom, and so it would be installed this way. Note that once the fan is installed, access to this trim pot is difficult, and so it's best to install initially just one screw so that the fan can be spun away from the trim pots and then pushed back into place. You must have this fan in place when you're tuning the card. It needs to be tuned as it will run, which will be with the fan in place. On that note, you want to make sure you don't tune these drivers to their very limit, because you'll find on a hotter day the drivers will still go into shutdown. So when tuning this card, either do it on a warm day or with the heater on, or don't have them right at their outer ability to stay online. One further jumper is the fan voltage selector. JP8 has 3 pins. Using a jumper to short the 2 outer pins will pass whatever voltage we're supplying this card directly to the fan connector. In our case, we're going to use a 24V power supply and a 24V fan, and so we'll set it up with a jumper on the 2 outer pins. If you had a different voltage supply or a fan that was capable of only handling 12 volts, you would use the inner 2 pins on this 3-pin connector. There's a 12V regulator on board which helps us produce the 0 to 10 volt signal and also power a very small 12V fan. You can't use this fan port to control any other 12V appliances. It's really only large enough to manage the fan and the 0 to 10 volt signal. I'm going to put this on the outside 2 pins. The fan connects directly below, and you'll notice a small positive and negative signal just below P19 where you connect the fan. Now to wire up the stepper motors. Going to follow the wiring convention shown here in the GRBL all-in-one instructions page, noting that all of our motor wires are in the same order other than the A motor, which will swap one of the pairs, in this instance green and black, to help ensure that the A motor spins in the opposite direction to the Y motor, which is required to make sure the gantry moves in the same direction. Being that our motors are facing each other on the Y, one has to spin in reverse. Using our 4-pin connectors, we'll wire up the two pairs really in any order, but we'll follow what we have on the all-in-one instruction page, which is black, green, red, and blue. We'll do this for the X, the Y, and the Z motor. Black, green, red, blue, black, green, red, blue, black, green, red, blue. Lastly, for the A motor, we're going to switch the black and green. So we'll start with green, and black. We only need to switch one pair. We've done that with the green and black, and so we can keep the original order of red, blue. This order doesn't matter whether we're working from the left-hand side of the switch or the right-hand side of the switch, or whether we're holding the, the connector, or whether we're holding the connector any particular way up or around, as long as we do it from the same reference point for each of the 4 connectors. You may also be using intermediary wires between the stepper and the connector to extend them to run through the drag chain, and those wires may not have the same 4 colors. It doesn't matter as long as your black and green from the stepper end up on one side of this connector and the red and blue end up on the other. Keep this A motor separate. We're going to plug in our X, our Y, our Z, and then A. X, Y, Z, and A. Lastly, our 24-volt power supply. Take note, the polarity is listed on the top of the all-in-one card. And at this point, we could power up the all-in-one. We can now power up the all-in-one card, and other than the fan spinning, we won't see anything else happen. Notice the motors aren't locked. This is because the all-in-one card does not supply 5 volts to the Atmel 328P, and so currently GRBL is not running and it's not sending an enable command to any of the drivers. By plugging in the USB lead, you'll notice an initial click as the motors lock and then a hiss as the stepper motors stay powered up. They're quite noisy and they do hiss and hum a lot. The motors are now all locked. All of our drivers are online. First thing we need to do is set up our current limiting to assure that all drivers stay online and are producing enough power to allow the motors to do the job. We don't want to tune them right to their edge of their ability, otherwise when a hot day comes along they'll go into over temperature shutdown on us. I'm going to move the fan out of the way so that I can access the trim pots. And I'll dial the current of one of the motors up by reducing the current limiting. We should see this motor go into thermal shutdown. You can hear the hiss and hum of the motors gets louder. And you can now see the A-axis is popping in and out of thermal shutdown. This can pop in and out all day. It's not going to hurt the driver, it's there as a protection. However, if that was to pop into thermal shutdown during a job, the machine will lose position. Anytime that driver is in shutdown, GRBL is instructing it to move and it's not moving, and it's therefore losing its understanding of where it is in space. And so we need to adjust all of these drivers to the point that there is sufficient power in the motor, but they're not going into thermal shutdown. I can dial up the current limiting slightly till I find a point that the motor will sit happily for several minutes without the red light coming on, and then we know we have an acceptable current limiting setup. We'd leave this here for several minutes to make sure no thermal shutdown lights come on. I'm going to go ahead and turn the current limiting back up to remove the hiss so that we can continue with the video. If we open up Universal G-code sender, choose 115200 as the baud rate and select our USB port. When we hit open, we should see a welcome with a listing of the GRBL's firmware and instruction to type $ for help. In the command tab, we can issue the $ command and get not much help. What we would like to do is put $, which gives us a list of all of the parameters that we're going to be working with to set up the machine. These parameters are all detailed in the GRBL configuration webpage. GRBL 1.1 configuration. I've got a listing here of what all of these settings are, and good reading to have a look through. It's not a big page and it's all very well explained. In the machine control tab, we have our jogging controls: X minus, X plus, Y plus, Y minus, Z plus, Z minus. 5 I have here is the step size in millimeters. that the machine should move when I click one of these jogging buttons. You'll notice that the X and Y commands are only moving the X and Y motors a small amount, and the Z command seems to be issuing a lot more. The reason for this is that the Z axis in our setup and commonly is geared significantly through a lead screw, where in this machine we're looking at now, the X and Y are belt driven and each step takes you a lot further in distance. Going to wait until these motors are actually connected to the machine to set up the directions and the step sizes any further. And before we move on to that, we'll connect a few limit switches. Our limit switches are all using a common ground, so I'll take one wire from each switch, join them together and connect them into our limit switch control port's ground connection. The pinouts again are shown on our GRBL configuration page. Connecting my X, Y and Z grounds all together. And then the second wire from each switch into the next 3 pins for X, Y and Z. This will be X, Y, and Z. We won't be connecting an A switch. GRBL doesn't actually support yet the extra Y-axis switch. It's a good idea to disconnect the power and disconnect the GRBL all-in-one whenever plugging in and out. Limit switch is connected. Powering back up. Anytime you disconnect the USB lead, you will need to reconnect to your universal G-code sender. To test the limit switches, the easiest way to check that you've got all of your limit switches wired up correctly, and it is very important to have the correct axis wired in correctly. Testing that you've wired up your limit switches can be done in one of 2 ways. If you're using the GRBL all-in-one card, there are little LEDs labelled X, Y, Z and A. We won't be using the A, but you should find that X, Y and Z limit switches illuminate the correct LED on the board. If you're not using the GRBL all-in-one card, another option is on the universal G-code sender to turn on the show verbose output option. At the end of this line, when a limit switch is depressed, you will see PN X, Y and Z. Make sure when you manually trip these switches by hand that the output here suggests that the correct limit switch is being triggered. Don't proceed until your X switch says X in this window or illuminates the X LED on the board. During a general machining operation, if any limit switch is tripped, the machine will come to a halt. So while it's not so important there, during a homing operation, the limit switch it's expecting to hit must be the switch that gets hit. Otherwise, that axis will continue and most likely crush the switch. I'm now going to remove these test motors and plug this GRBL all-in-one card into a CNC router to continue with the setup. I've now connected all of those motors to an actual CNC router, and we're going to go ahead and look at some of the parameters that we need to set up to set the directions, speeds and limits for these axis travel. I've also downloaded a nightly build of the Universal G-code sender in the meantime, and I hope it all goes smoothly because I haven't used this one before. Again, we're going to choose baud rate 115200 and our USB port and open. UGS pops us out a list of all of the parameters that GRBL has set, and we'll need to adjust quite a few of these in order to get everything set up correctly. Initially though, we'll turn on the show verbose output so that we can see if our limit switches are connected to the correct ports. If I trip the Z limit switch, we can see that pin Z has turned up in the output, which is correct. Trip one of my X switches, and good, P and X. I'll now trip one of the Y limit switches, and Y is showing up in the verbose output. So our limit switches are set up correctly. Now, in the command, if we type $, we get our listing of parameters back again. $, enter. Some of the important parameters that we'll need to look at straight away are step idle delay. We'd like to set this to 255. Step idle delay is the amount of time after which the last step command was sent to the drivers that they'll go into shutdown. We want to keep them active all the time so that they're always locked. This helps us with, for example, changing a tool. We'd like the machine to stay locked so that we don't accidentally move it while we're putting a new end mill in. You can change this setting with $1 equals 255. Going to look for hard limits. $21. It's currently set to 0, which means it's off. Hard limits are our limit switches, and we'd like to turn them on. So $21 equals 1. Now that our hard limits are turned on, we'll find that any time a limit switch is triggered other than during a homing cycle, Universal G-code sender and GRBL will error out and need some attention in order to get the machine started again. As you can see, alarm 1, reset to continue. If that were to happen during one of your operations, there is no way to easily restart the job. The machine needs restarting and rehoming. I can hit soft reset to restart the GRBL firmware, and you'll notice that now that I've turned the limit switches on, the hard limits on, the machine will always come up in an active state alarm. You can use $X to clear the alarm. Going to have a look at our motor directions now. X minus and X plus should move the X-axis left and right. X minus towards the left. I'll set a step size of 10 millimeters. and I'll try X minus. Great, it's going in the right direction. It looks like it may have been moving slightly too far though. We'll address that in a minute. Y plus should move the machine away from me. And it doesn't. So we can see that our y-axis is traveling in the wrong direction. We'll have a look at Z. I'll set it for 2 millimeters and choose Z minus. This should go down. Great. So it's only our y-axis that's moving in the wrong direction. Let's have a look at how to fix that. Back in a command prompt, $$ again to bring up our parameters. We're looking for a direction invert mask parameter, $3. It's set to 0 now, which suggests don't do anything. If we have a look at our GRBL 1.1 configuration, scroll down to the $3 parameter, we can read about how this works. There's a table here that shows how we can invert directions. We only want to invert the y-axis. It's the only axis that we had going in the wrong direction. So we're looking for a no, yes, no, which is here. Which means we need to set 2 as the value of our step direction invert mask. So $3 equals 2 should change only the direction of the y-axis. Just check that the x hasn't changed. No, x positive is still going the right direction. Check the z-axis. Z minus is still going down. Hopefully now our y plus is going backwards. And it is. So you could have gone into our motor wiring and switched some of the motor wires to make the axis run in a different direction, but it's much simpler to fix it in software here, and for that reason we didn't have to pay too much attention at how we wired the motors up. If you found when moving the y-axis that the gantry is crab stepping, it means that you didn't correctly ensure that the 2 Y motors were traveling in opposite directions to each other, and you'll have to go and fix that with motor wiring by swapping one pair from one of the Y or A motors. Next we'll have a look at the steps per millimeter. Different machines will require a different number of steps to move that axis 1 millimeter, and different axes on the one machine will also require possibly a different number of steps per millimeter. Looking in our parameter list, we have $100, 101 and 102. These are the number of steps it will take to move 1 millimeter. With the AT5 belting I'm using on this machine, it's somewhere around 40 steps per millimeter to move the X and Y axis, so I'll update those now. The Z-axis is around 188 steps per millimeter. It's a lot higher because the Z-axis is geared through a lead screw. We should also have a look at our maximum rates here. This is $110, 11 and 112. At the moment they're set at 500 millimeters per minute, which is fairly slow, but is probably a good start for just while we're tuning the machine. It should give you enough time to get to the emergency stop button if you click the wrong button. Accelerations are 120, 121 and 122. At the moment they're defaulting to 10 millimeters per second squared, and they can probably be moved up to say 100, 130. Our maximum travel, these generally get in the way. If we've got hard limit switches on both sides of every axis, you can just turn these off, and you do that by setting $130, 131 and 132 to a value much larger than the machine, so that they stay out of the way. Otherwise, if you're using an X-carve or a machine that only has a single limit switch per axis and so can only tell if it's in trouble going in one direction, then you should set up the soft limits to ensure that if you instruct the machine to go further than it should, it will know to stop. The first thing we do when we turn on the CNC router is to home it, and so we should have a look at the homing settings. They may or may not be moving in the right direction. We can adjust them similarly to the way we adjusted the direction of the motors initially, but using a different parameter. It's the homing direction invert mask. It works the same way. To begin with, we set each axis to about the middle of its run, so that we're able to issue a home command, and if something seems to be going in the wrong direction, we can hit the emergency stop or pull the power before it creates trouble for itself. I'm going to hit the $H button to issue a homing cycle to the machine, and what I expect to see is my Z-axis going up. If anything other than that happens, I'll hit the E-stop or reset the machine so that we can assess why that didn't happen. I haven't enabled homing in the settings, and so it just errored out. Let's have a look at the settings again. Homing cycle enable, $22. It's set to 0, which is off, so $22 equals 1. Our homing cycle is now turned on. There's one other parameter we should have a look here at, which is the homing pull-off. It's $27 and it's currently set to 1. This should be increased to at least 3 millimeters. Homing pull-off is the distance to which the machine will pull away from the limit switches when it's finished the homing cycle, and also the distance it will pull away looking to find the switch depress. If you don't pull far enough away from the switch during the homing cycle that the switch is depressed, then the homing cycle will fail. I should now be able to issue a $H command. And the homing cycle completed successfully. Convention was that flatbed routers home to the back right hand corner of the machine, and everything forward towards the front of the machine and left was the negative space. Some of the CNC machines you find now, like the Shapeoko and the X-carve, like to home to the front left-hand corner of the machine. And if that's your preference, then you can adjust values in the homing direction invert mask, $23. It uses the same table that we were looking at for the motor invert mask. And in this instance, if I wanted it to come towards the front left of the machine, we would need to change the direction of both the X and Y axis. Z is correct, it'll always go up, but the X and Y, to invert X, Y and leave Z alone would be $3. So if I change $23 equal to 3, when I home again, we should end up at the front left-hand corner of the machine. I've restarted the machine. We're not going to wait for it to home all the way to the front left, but you can see it was moving in the right direction. So that's the basic setup. We've set up the GRBL all-in-one. We've got it connected to Universal G-code sender. We've set all the limit switches up and confirmed that they are triggering on the right switch. Set the motor directions, adjusted the speed and steps per millimeter that the motors will run at, issued a homing command. There are a bunch more parameters in GRBL that you should have a look at, and you will likely want to increase a lot of the feed rates. Be careful not to increase the homing speed too much. Anything more than about 1 meter a minute gets dangerous, because we are going to hit these limit switches, and if it happens quickly we could crush the limit switches.